The purpose of this video is to show how we can use integration to find volume. We're going to start with a basic shape like a cylinder to get the idea, and then move on to a cone, and then you'll be able to do like a sphere on your own. The idea of using integration for these problems is cross-sectional area. So if I was to look into the shape at this side, at the very start, I would have a circle. If I was to cut the cylinder in half and look at what comes out when I look on the top of the bit that I cut, it would be a circle of the same size. Right at the end would be a circle as well. So what I'm trying to find to be able to find volume is a function of the cross-sectional area. Okay, and we're going to call this a of x. So I start on one side of the shape, typically the left-hand side of the shape, at x equals 0, and I'll go to x equals 20. So what I want my graph to show is the relationship between the area and where I am on the shape. Since I can see here from these three diagrams that my area is always the same, in this instance my cross-sectional area will be a straight line. What will be the value of the straight line here? Well, it'll be a of x is pi r squared. Okay, this radius is 5 centimeters, regardless of where I am on the cylinder. So pi times 5 squared will give me 25 pi. So regardless of where I am, this is 25 pi. I'm trying to find the volume of this shape. Remember, I know that volume equals area of the base times the height. Okay, so in this scenario, my area of the base would be a of x times the height. Okay, and I know that a of x is 25 pi. So if I was to go from 0 to 20, okay, why 20? Because that's how tall or how long the cylinder is. I could use this cross-sectional area that I'm shading to find the volume of the shape. Why? Because this side is the area of the base, and this side is the height. So essentially, I can write down my understanding that the area under the cross-sectional area is the volume. Okay, so let's make sure it works. Okay, remember 25 pi times height. I'll have 25 pi times 20. I'll end up with 500 pi. Just doing the calculations normally, 500 pi centimeters cubed. Let's try integrating the area. So the volume is integral from 0 to 20 of my area function. Now you might think, oh, it's just a rectangle, I don't need to do this. It's good practice for when it gets harder. So integrating from 0 to 20 of my area function, which is, well, regardless of what x is, the area is 25 pi. It doesn't matter if x is 0, x is 10, x is 20, I'm always going to have 25 pi as my area. So I'm integrating 25 pi dx. Remember, 25 pi is just a constant, So it'd be like integrating 3 dx, which would be 3x. So integrating 25 pi will be 25 pi x from 0 to 20. Substitute in the bounds, 25 pi times 20 minus 25 pi times 0. End up with just 25 pi times 20, or 500 pi centimeters cubed. Exactly the same as what I got using the standard volume formula that we've learnt, for all of our life, area base times height. So this shows that this understanding area of under the cross-sectional area curve is the volume, and that's an okay thing to use. Let's go on to something more interesting, finding the volume of a cylinder. And we're going to use the same process. We're going to try to find a formula for the cross-sectional area from x equals 0 to x equals 20. Already we can tell that the cross-sectional area is not going to be constant like it was in the previous example. At x equals 0, we have a small dot. At say x equals 5, we've got a circle that's starting to get big. At x equals 20, a bigger circle, up to, at x equals 10, a bigger circle, until x equals 20, where we've got a big circle. I need to find what that relationship is. Okay, so I need to find a of x. If I was to give it a brief sketch, I'd know that it'd start at 0, end at some big value. I'm not sure what's happening in here. Could be doing heaps of different stuff to get between those points. So I'll need to find some relationship between how far into the shape I'm going and the radius. So about halfway through the shape, I'll make a little right angle triangle here, and I'll call this the radius, okay, which will be the radius of all of these little circles that we're cutting through there. I've gone into the shape a distance of x. So I have this small triangle, okay, R and X. Okay, I probably should have drawn it the other way, but I also have this really big triangle which has dimensions of 5 and 20. Okay, the really big triangle. So I'm going to use the idea of similar triangles to try and find some relationship between R and X. Okay, since these triangles are similar, okay, because this angle is the same, I can say that the ratio of R on X is the same as the ratio of 5 on 20, okay, because these sides are corresponding, okay, just by similarity of triangles. From here, I can rearrange to get an expression for R. So let's do that. R on X is a quarter. So R is really X on 4. So we can see now how the radius is changing as I move further into the shape. Okay, it's dependent on how far I've gone in, and it'll always be a quarter of how far I've gone into the shape. So if X was 1, R would be a quarter, and so on. I remember my goal was to find a formula for the cross-sectional area. I know that the cross-sectional area is going to be pi r squared, because I know that they're all circles. Okay, thankfully I've made a relationship for r, which is x on 4. So pi x on 4 squared is my cross-sectional area. Okay, and to make this a little bit tidier, expand the squared to both of these. X squared on 16. Okay, and I've got my relationship for cross-sectional area. If I was to give this thing a graph, okay, it's a quadratic equation going from 0 to 20, okay, and end up at this point, pi times 400 on 16, a quadratic equation. Quadratic equation, so looking something like that. Okay, here's our a of x. Okay, the good thing about these models is we don't necessarily need to graph them. Okay, we just need to use the relationship that the volume will be the integral of the area function between the bounds, okay, between 0 and 20. Okay, I'll go and integrate away. So integral between 0 and 20 of pi x squared on 16 dx. I'll bring the pi on 16 out the front. Okay, just make it a nice constant inside to play around with. Pi on 16 x cubed on 3 is my integral. And I'll be left with pi on 16 times the difference between these two things when we substitute in the bounds. Okay, so I'll end up with 20 cubed pi on 3 times 16 as my volume. I'm sure I can probably simplify that some more. And I'll end up with something like 500 pi on 3, and the units are centimeters cubed. Okay, you can check that this is correct. Okay, using your normal formula for volume of a cone, which is 1/3 by r squared height. Okay, slot all these values in. Correction, the radius is 5. Okay, we'll get our 500 pi on 3 centimeters cubed. Exactly like we got using this integration idea. Okay, so flick over to some of these problem solving questions. There's some pretty nasty ones in there. Probably recommend doing these two. Probably do question 8 first and then help yourselves.